Okay, good morning all of you. My screen is visible. Anybody? Hello. My screen is visible, ma?
Yes, sir.
Okay. See, we will see today three-phase full converter. Yesterday we observed that three-phase semi-converter, it will give only the first quadrant operation. That means whether it is R load or RL load, anything, it will give only the first quadrant operation. So you can see the quadrant operation there, voltage and currents are positive. So this is the irrespective of the load, we can get it as a current and voltages are positive. But whereas now it is a fully controlled converter, it is a two quadrant converter. You can observe that if alpha is less than 90 degree, it will give as a first quadrant. Alpha greater than 90 degree, it will give as a fourth quadrant operation for RL load. R load case, voltage and current is positive because R load, voltage and current are in phase. That's why whenever supply voltage is reaches to natural zero, current also be the natural zero. So therefore thyristors will be open naturally at pi. That's why it will never give as a negative voltage. So that is the major difference between R load and RL load. RL load case, some energy is stored in a inductor, that energy is going to be dissipated. So that is the reason you can dissipate after pi. That's why you'll get it as a negative voltage. So these are the two things. And now once if you compare with what you call it as semi-converter, in a semi-converter we can notice that upper group is positive group device, that is a thyristors only, but in a lower group device is a diodes for the case of semi-converter. But now in full converter, simply replace the lower group devices by thyristors, will make it as a fully controlled converter. So, but for R load case, if you notice R load case, whether it is a semi converter or a full converter, both will give the same output. But why we want to go for as a full converter, the question is. But the full converter will give the fourth quadrant operation also. That means it is a two quadrant converter. Full converter is a two quadrant converter. Semi converter is a one quadrant converter. That means this is a rectification mode of operation. This will give rectification as well as the inversion mode of operation. So that is another comparison. And another one, whenever you require only motoring, you have to go for semi converter only, not preferred the full converter, because full converter is a costly one when compared to the semi converter. But whenever you require two quadrant operation only, you can go for as a full converter. Two quadrant means it is a motoring operation as well as the braking operation. In terms of drive, if you call it as when it goes forward motoring, and then whenever you want to stop, then you can apply as a inversion mode of operation, that is a braking operation. That means that motor will not rotate in the backward direction. What we want to do is we apply alpha greater than 90 degree, it acts as a inversion mode of operation. The sharply motor speed reduces to the zero level, and you can apply the mechanical brakes and all, normal traction application and all. But now there is another important difference in the semi converter and full converter. In a semi converter, you can see it is a three pulse converter, three phase semi converter. It is a 3 pulse converter, but full converter it is a 6 pulse converter. What is the difference here? You can see in a semi converter, upper group devices are the thyristor. How many thyristor? 3 thyristor, 1, 3, 5. And lower group devices are the diodes there. That's why we required only 3 pulses. By default, lower group devices are going to conduct whenever it imposes a negative voltage. Whereas in the full converter, we can see that upper group also thyristors, lower group also thyristors. Totally 6 thyristors are there. That's why we need to provide 6 firing pulses. IG1 to IG6, we need to provide the firing pulse. Whereas in the previously we mentioned IG1, IG3 and IG5. These are the firing pulses. But now we need to provide all the 6 firing pulses 1 to 6. And now the remaining logic is same. What is the remaining logic? You can see that whenever the device, you can see there is a T1 want to fire, the A phase must be more positive than other phases. Then only T1 will forward bias. Similarly, T4, both are in the same leg, no? So T4 will get forward bias whenever A phase is more negative when comparatively other phases. Like that, all other phases, let it be B phase. So whenever B phase is more positive, T3 will forward bias. Same B phase is more negative, T6 will be forward bias. Similarly, C phase. So here is very clear cut process. Whenever the phase is having as a more positive, then upper group devices will forward bias, and that phase is more negative, then the lower group devices will get forward bias. But now, when compared to semi-converter, in the earlier version, in the semi-converter case, if it is a more negative, automatically lower group devices will start conducting. But now, lower group devices also as a thyristors. That's why what we want to do is, whether when the thyristor is having more negative, means A phase or a B phase or a C phase, any phase, if it is a more negative, that is only the forward bias but not conducting. When it will conduct, whenever if you pass the gate signal for the lower group devices also, it will start conducting. That's why, like how we noticed in the case of semi converter upper group devices, same fashion you must see, even though that particular phase is more negative, it won't conduct. You have to check one more condition, whether that phase is having firing pulses or not. If firing pulse is present, then only the device is going to start conducting like upper group devices. That is only the reason. Now we'll see the what you call it as supply as well as firing pulses, then how to represent the output voltage waveform, then we'll see the average expression, RMS, all these things. Once if you know the average, simply square it and whole power 1 by 2. If you do that, we'll get RMS also. Now, suppose if alpha is 0 degrees, means in instant, alpha is 0 means what? It's like a diode, nothing. Or you can get it as a maximum output voltage will be obtained whenever alpha is equal to 0. As usual, supply you have to give here ABC. Once if you give the supply, then automatically corresponding devices is going to be forward bias based on the magnitude of the supply. Means whether it is a more positive or a more negative based on that. The sequence will be fixed here. 135462. If that is the case, conduction always 1 2 2 3 3 4, then 2 3 3 4, then 4 5 5 6 6 1, then cycle will repeated again 1 2. So how many totally? 1 2 3 4 5 6. So these are the 6 devices. We'll start 1 2 2 3 here, 2 times 2 3, then 3 4 4 5 5 6 6 1. So these are the total 6 intervals. What is meaning of in that is 6 pulses will be obtained in the output. 6 pulses will get it in the output. Then how many degrees each pair of the devices will conduct? Pair means here either 1 2 device is 1 pulse, or 2 3 is another, then 3 4 like that. So each pair will conduct how many degrees? Total is a one full cycle is 360 degrees. So that's why 360 by 6 pulses. That means 60 degrees. This is important. Not when compared to 3 pulse converter. We noticed in a 3 pulse converter, 3 pulses in the output except maximum. Maximum is alpha is 0. We'll get 6 pulses there also. But that is only for the maximum output is same. Whether it is a semi converter or a full converter, but only will differ other than the maximum. Now in a 3 pulse converter, total one full cycle 360 by 3 pulse output. So then what will happen? 120 degrees is going to conduct the each pulse. Now here 120 instead of 120, the pair of the devices is going to conduct 60 degrees. That means one is upper, one is the lower group will conduct. That is must. Otherwise it won't close the loop. So output will be connected directly line to line. Here you must remember one thing. Output voltage is always line to line voltage. In case of bridge type, or in case of midpoint type, your output voltage is always phase voltage. So this is the another different you can notice. Now we'll see that alpha is 0. What you have to draw first? You have to draw the supply voltage. That means 3 phase supply voltage you have to draw. After that you have to identify the crossovers. Then you have to provide the firing pulses. Then you have to shade the output. That is the sequence of the graph representation. Now I draw the just see that there is a supply voltage. This one is a 3-phase input. So whatever we mentioned here, that is a 3-phase input voltage. Now for this, what I want to identify first, crossovers. How many crossovers you have to identify? For these 6 thyristors, 6 crossovers are required. Now in which crossover is related to which device you have to identify. For any device, that phase voltage must be more positive. You represent that upper group device. If that phase is more negative, then you can represent as a lower group device. So now you can see in this case A phase. Let it be red one is A phase. That A phase device is this point onwards. It is a more positive. That's why represented is a T1 here. That means A phase more positive is connected to anode of a T1. Same A phase, if it is a more negative, then what will happen? You can represent that crossover is a T4 crossover. You can see same thing. A phase is started here, then it is getting up to this is lower and it reaches this point, then it is a exactly same, that is a reference. From there onwards A is more positive. That's why you can notice that this will be as a, now what you call it as T1 reference. Same thing, you come down, it reaches to the 0 and then it started negative. Then when is more negative, but this duration is a some other phase, means C phase is more negative, but after this point you will get it as a C phase is more negative. That's why This crossover I represented for T4 thyristor. What I did, very simple logic. If IA phase is more positive from that crossover point represented as a T1, same from this point onwards, you can notice that this area totally more negative. More negative it is connected to T4. More positive it is connected to T1. Similarly, T3. T3 and T6. What is happening there? B phase. So B phase is more positive represent the T3. More negative represent T6. Now I will consider as a B phase. Let it be, it started here, and then from this point onwards we are getting as a more positive. So that's why this area I will represent as a more positive connected to T3, and similarly, and from this point onwards it is getting down, and then here onwards it is a more negative. Then what will happen? This portion we can represent it as a T6, because more negative portion will connect it to the T6. That's why it is a reference point for T6. Similarly, C phase. C phase, you can see it started here and it is coming like this. This point is a common point. From this it is a C phase device, more positive. That's why we connected as a T5. And same thing, you can see the negative side also. This is a negative portion. In a negative portion, it started here, and up to this some other phase, B phase is more negative than this. That's why we will get this point is a common point. From here onwards, we will get it as a more negative. More negative means T2. That's why T2. So like this, you can represent the crossovers. Are very straightforward. Upper side are one T1, T3, T5, because A phase, B phase, C phase. But lower side you can see this green is a C phase line that is connected to T2. That's why I make it as a T2 crossover. And this red line is represented as a phase. A phase lower group is a T4. And then blue line represented as a B phase. B phase lower group is a T6. That's why we represent a T6. That's all. So like that we have to identify the crossover. So that point also over. First you have to draw the circuit, three-phase fully controlled rectifier. Then you have to represent the waveform, that is a ABC or RYB any notation. You have to represent three-phase waveform. While you are drawing the waveform, it is simple way to represent parallel lines. You can draw each line 30 degrees, like what I drawn the graph sheet similar fashion, and start at 0 and 90 you can put it as a peak, and 180 again 0, and again 270 put it negative peak, and then 360 0, and you join all the points. Then give it as a phase shift of 120 degrees, and same manner put it as a 3 lines is a peak, another 3 lines 0, like that, and you join all the things, you'll get it as a clearly 3-phase AC supply. And now we identify the crossovers. Then what next we have to do? We have to provide the firing pulses. How many firing pulses we have to give? Totally 6 firing pulses. As you know that here there is a line, and you can want to represent, let it be as a 3-phase supply firing pulses. All 6 firing pulses we have to draw. So let it be, it is a T1, T2, like that, any totally 6 we have to draw. Now we can consider for 0. I want to represent the T1, T1 let it be. How to represent 0? We start at this line, and where it will end? Natural 0. And again the cycle is going to be repeated for here, and this will be like this. And how to represent the T2 pulse? So T2 crossover is this. From this point is our reference, and when it is goes to the natural 0, this point. So you can represent as a firing pulse for T2, and similarly for T3. Then T3 is upper side. We can start here, and where it will end at 300 degrees. Then again at T4, the 4 is lower side. We can start here, and it will be ended at natural 0, and then T5, 5 is upper side, you can start here and ended here. So this gap you can count, can we started here the pulse, no? This and ending will be natural 0 here, and again pulse will be started here. Then what is the duration? 1, 2, 3, 4, 5, 6, 7. So after 7 you can repeat this side also. So whatever pulse is available, and similarly T6. So like this we have to provide as a firing pulses. I will show that pulses like this. First one, T1, it is combination. You want separate lines, you can represent, that is also fine. I will show that separate line in the graph sheet also. We started at alpha is equal to 0. So this is the starting point, and then ending point will be, because another pulse is presented here, even if it provide the pulse completely also, it won't affect anything. If you want to draw separate firing pulses, you can provide like that. So you can start that pulse 0 axis, and ending will be up to natural pi. You can put like this for T1. Similarly all other. But here we mixed that pulses. That's why whenever even pulse is available also after this for T1, it won't be impact, because T3 is going to fire. That's why they stopped pulse here itself. But naturally we'll start with the reference point or alpha and end with natural pi. Now this is the duration. T1 is more positive. We represented T1, and this is the duration. T3 is more positive. Then we'll represent the T3, and again this is the duration for T5. So that is the case. We represented upper group T1, T3, T5. So before that, automatically cycle is going to be repeated. No, after T5, T1 will come. No, and before T1, what is that? T5. That's why we mentioned T5. Or you can see that this is the more positive than other phases. More positive C phase. C phase is more positive means T5. No, that's why we represented as a T5. Similarly, for negative group devices, negative you can see this is starting point, and up to here it is a more negative. Which phase? This phase is C phase. C phase is more negative means T2. That's why we represented as a T2. And the red one, it is a more negative from here to here, means Q to R. Red one is more negative. Red is VA, and VA is connected to T4. That's why we represented T4. And then blue will represent this is more negative. That will connected as a B phase. B phase more negative is T6. Then again what will happen? T2 will conduct. So before T2, T6, no, or you can see here this one is a B phase. B phase is more negative. This duration, which we who will conduct? VB. VB means lower group. So T6. So that's why you represented T6 like that. It is very simple way to represent firing pulses. The duration, the more positive you will represent that T1, T3, T5, and more negative T2, T4, T6. And then suppose if I want to provide as a firing pulse for alpha is equal to 30 degrees, then what you have to do? Same, if this is alpha is equal to 0, whatever I represented now. And now if I want to change to alpha is equal to 30 degrees, what is the modification I have to do? Very simple modification. Instead of starting here, you can start this. That's all. And again this, and again here. Whatever I drawn red one, that is the starting pulse. Then what is the pulse? It started here, ended will be here, and again this is starting, ended will be here, and starting, ending will be here. So like this. Similarly, T2 phase. Instead of starting this point, whatever it is there, I am striking out. That is not a starting point for alpha is equal to 30 degrees. Now for this case, what is starting point here for T2? We'll get like this, and instead of that we'll get like this. That is a starting point. So now we can represent the starting points will be like this. Then that is alpha is equal to 30 degrees. Suppose alpha is equal to 60 degrees, what you have to do? Again you can start here. All the cases, one more 30 degrees will shift. Instead of here, it will start here, like that. So that is the way we have to change the firing pulses. Now, first we'll see the alpha is 0. Now, everybody is clear this. Just we have to draw the three-phase supply, identify the crossovers, 135, then 462 crossover. In that, which is the more negative portion, you have to see. This is not a this order. You see that 135 here ABC, that's why. But lower side, which is more negative, starting B phase is more negative, that's why T6 in this duration. Then C phase is more negative, then T2. Then again A phase is more negative, then T4. Like that, we can able to represent the lower group devices crossovers. Now we have to draw the line to line voltages. As I said earlier, line to line voltage are shifting as a 30 degrees. Once if you shift that 30 degrees, then you can draw the AB, AC, BC, BA, CA, CB and again AB. Cycle is going to repeat it. This is the case of what you call it as line to line voltages. Now we have to draw the output voltage waveform. How will you draw? It is a very simple logic. Even when compared to what you call it as a semi converter, this is very simple. We started this. You can see there is a firing pulse for T1, and once at any instant you can able to identify which devices are going to be forward bias. Suppose this is the instant I want to know. Tell me anybody what are the devices is going to forward bias. If you know the device number, you can easily know the output voltage because it is passing through that devices only current. That's why suppose at that instant which is more positive, A phase is more positive and B phase is more negative, and A phase is more positive, B phase is more negative. Then which device will start conducting? Current will pass like this, goes to T1 or load, then it goes to 6 to out. Then what is your output? Based on your device conduction. So it goes T1, that means A phase, and coming out to B phase. So that one will be as a B. Then your output will be VAB at that instant. Similarly, any other instant you can able to find. Suppose I want to know at this, at omega t is equal to 60 degrees, let us assume. What is your output? A phase is more positive and then B phase is more negative. So AB only will conduct. And similarly, some other instant we'll see at 120 degree, omega t is equal to 120 here. A is more positive, but C is a more negative. What is your output voltage? VAC. But you must see that even though C phase is more negative at this instant, we have to observe that C phase device is a T2. T2 having firing pulse or not. You can see here, you coming down and check the pulse. If you come this dotted line, you see that pulse is available for T2 in this area. That's why it is going to conduct. If not, then what will happen? Only previous set of devices is going to forward bias. Now, I want to shade the output voltage based on the firing pulses. I started alpha here. Then according to this, A and B is more positive and more negative, and that's why your output will be AB. Then how long you have to check it? Every 30 degree you can check it. Here you can see still AB is more positive and more negative, A is more positive, B is more negative. Again, A is more positive and B is more negative from this point onwards. What you can do? A is more positive, but lower group device is going to change. Instead of B phase, now C phase is having more negative. Whether I have to transfer to C phase or not, you have to check with the firing pulse. Now C phase device is T2, T2 firing pulse is available from this point onwards. That's why your output become VA and this lower group devices are C. That means VAC is your output voltage. So like that you can make it as an output transfer to AC. Again you can check it. Upper is positive, lower is still negative. then AC only you can shade. Once this point reaches, what will happen? Then this point reached, this is a crossover, and from this crossover onwards, A is a less positive than B. And whether I am to transfer to A phase to B phase or not, that decided by what? Firing pulse. That firing pulse you can check it from this line, you can come down and you can see this one we call it as a lower group device, upper group device T3 pulse is available. That's the reason A magnitude is less than B, therefore B is a forward bias, but pulse also available, therefore the output will transfer to, instead of AC to BC, because C is still negative, it won't change anything, but only A is going to be transferred to B, because magnitude is going to change and pulse also available. Then you can shade the BC, then you can shade the BA, and so on. You can able to get it as a all 6 firing pulses. So this is the way we can represent all the 6 firing pulses. So you can count first AB. Now you want to can check the order also. Wherever you can start from that onward, sequence will repeat. So AB, then which devices is conducting? 6 1, then 1 2, then 2 3, then 3 4, then 4 5, 5 6. Again 6 1. Cycle is going to repeat. So like this, the devices is going to conduct. So all the 6 firing pulses will be obtained in the output. Then your output voltage will be 6 by 2 pi, and integral limits you can apply alpha plus 30, and ending you can see any one pulse you can able to fire. This pulse is a how many degrees? 30 plus 30, totally 60 degree. The question is, each device how many degrees it will conduct. So alpha, I am asking whether it is a T1 or a T2 or anything. Each device, this 60 degrees is pair of the device. Pair means here T1 as well as the T6, or here T1 and T2. So these two T1, T2 will conduct together is 60 degree, and here T1 and T6 together will 60 degree, and then T2, T3 will be 60 degree. Now my question is, each device T1 how many degrees is conducting, T2 is how many degrees. That means here T1 is there, here T1 is there, and similarly T2 is here and T2 is there. That means 2 times each device is going to conduct. That totally 120 degrees each device is going to conduct, but pair of the device is going to conduct only 60 degree, or each pulse duration is a 60 degrees, but each device will conduct 120 degree. Now what next? We identify the crossovers, then we provided the firing pulses, then this is the line to line voltage. By shifting 30 degrees, again you redraw the 3-phase supply and make it positive to negative, negative to positive. We'll get all 6 line to line voltages. And now you can able to see the currents also. So this is the alpha is 0 degrees. Whatever I drawn here, that this portion you can draw separately. That only the next slide what I shown. You want to can draw directly this separate portion also in exam. If they didn't ask line to line voltage, wire impulse representation, all these things. If they ask draw the output voltage waveform for alpha is equal to 30 degrees, then draw the supply and then make it as a 30 degree waveform shape. That is also correct, but to clear cut understanding, you have to provide the firing pulses and draw the line to line voltage and represent the waveform. That is a complete question. And now you can see that supply, then we represented the output voltage waveform, and the elect load current is constant magnitude. That is our assumption, and you can make it as a straight line. And these currents are the current thyristor currents and then source current. What we can represent, whenever thyristor 1 is conducting, you can represent the current because it draws current from the source. Now where to where thyristor 1 is conducting? A. 1 is means A, no? Here and here. From here to here, thyristor is conducting. That's why I make it as a current. waveform will be like this. And again, when the thyristor 1 is conducting after one complete cycle, so from here onwards thyristor 1 is conducting. That is the reason I make it as a like this. Suppose if you want to make it as a thyristor 2 or thyristor 3, anything based on in which instant that corresponding thyristors is going to be forward bias or conducting, there you represent the current. This is the thyristor 1 current. Similarly, I want to represent A phase current or a B phase current or a C phase current, anything. Now A phase current, whenever A phase device is conducting, then current drawn from the source. Suppose T1, A phase is means what? Here we have two thyristors no, for A phase, T1 and T4. This is for A phase. So there is a A. So then T1 and T4 is going to conduct. So whenever T1 is conducting, your current positive, and whenever T4 is conducting, your current is negative. That is only the A phase waveform. So T1 is conducting 120 degrees and T4 also conducting 120 degrees. So during that instant, if T4 is conducting means it is a more negative, no? During that instant it will conduct, that's why current drawn from the source also negative. We'll get the current waveform. A phase current waveform like this. Similarly B phase and C phase only 120 degree phase shift. So this is the current waveforms for particular instant. Now we can represent positive for this duration because T1 is conducting here and here is a T4 is conducting. That is the reason we will represent it as a negative. This is for IA, A phase current. Similarly B phase it is shifting. So B phase means T3. So wherever T3 is conducting, there you can represent as a positive and then connected to 6 because 1, 3, 5 and then here is a 4, 6, 2. So B phase 3 and 6. Wherever 3 and 6 is conducting, there you can represent as a positive and then negative like this. Similarly for C phase. So T5 is conducting, then positive and negative. So like that you can represent all the phase currents also. Now we want to derive the expression, we can easily derive also and you can see the average. How will you get the average? Each SCR conduct for 120 degree. I mentioned already. Each SCR is different. Pair of our pulse is different. Our pair of the devices are different. That's what I mentioned earlier. Total 360 degrees. Pair means only 6 pairs are there. These are the pulses. So 6 pulses. That's why each device will conduct 60 degrees. But each pair of the devices will conduct 60 degree. Each device means here T1 is conducting, here T1 is conducting. Or you can see that T3 is conducting here and here also T3 is conducting. That means 60 plus 60, 120 degree. So that is the way we represented average 120 degrees of each device by 360 degree. Total current is I0 current. So I0 by 3 is your average thyristor current. And RMS just root. So and that will give as a I0 by root 3. And we can see the another one, each phase conduction. Each phase means this one, whether it is a IA or IB or IC. Each phase how many degrees is conducting? Here is 120 degrees. This portion is 120 degrees. Totally 240 degrees. Each phase is going to conduct. That's what I mentioned here. Each phase is conducting 240 degrees. So 240 by 360 into I0, that will give as a RMS phase current. And earlier it is a thyristor current. Now peak inverse voltage. So that is a root 3 into Vm is your peak inverse voltage. Now, so this is the case of alpha is equal to 0 degrees. Similarly, alpha is equal to 30 degrees, 60 degrees, 90 degrees, R load and RL load, everything will similar. Now I will show that all the things also I will explain. Even for RL load, what will happen after a continuous mode of operation, normally we will get it as a 0 in case of R load, means after natural pi, If pulse is not available, then the thyristor will remains open, then the current is 0 remains. That's the reason we'll get it as a discontinuous. But now, if you use RL load, wherever discontinuity will get, that previous conduction only will takes place because of energy stored in an inductor is going to be dissipated in the same thyristors. That's why we'll get it as a negative. That is only different between R and RL loads case. RL up to continuous mode is both the same, and for discontinuous mode of operation, that will become as a negative. So now we can see alpha is 30 degree as usual circuit diagram. Why I am repeating this different values of alpha? In exam they may ask the specific alpha. Generally, if they ask, we explain the three-phase fully controlled converter, or you can say that or derive the expression for average output voltage, all these things you can do it. But draw the waveforms for alpha is equal to some 30 degrees or 60 or 90 or 45 or 75, anything they may ask. That is the reason I am giving lot of alphas with variation of alpha, how to draw the output voltage waveform. Now, as usual, what is the modification we noticed in this supply waveform? Anybody you can see that same supply you have to draw, but crossover points is fixed all the cases T1, T3, T5, but the point of alpha will differ. These are the crossover for T1, this is T3, this is T5 crossover. That crossover means that alpha is equal to 0. Whatever if you represent this crossovers, that is nothing but alpha is equal to 0 instants, and all crossovers will give alpha is 0. And now I want to put the firing pulses for alpha, different alpha, suppose 30 degrees. Then what I have to do? This is 0. You count 30 degrees, will give the firing pulse. The starting point is here for T1. Similarly, for T2, this is 0 and 30 degrees. This is for starting point of T2. This is the starting point of T3, because this is the actual reference, but you counted 30 degree. Similarly T4, similarly T5, then T6. So all the things only we need to shift the 30 degrees. Now we can see that pulses when compared to alpha is equal to 0 pulse and this pulse, the different point is earlier alpha is equal to 0 instant, we started the firing pulse is here. This is the firing pulse, but now we start the firing pulse will be previous one. So this is the pulse for T1. So now like that all other pulses. This is T3 starting now. You count 30 degrees, we'll get here firing pulse. T5 0 and 30 here. Like that, any value of alpha, one small different in this providing the firing pulses, only you can shift that durations. So delay angle. Instead of here, you can shift here, that will become as a 60 degrees. You shift up to here, it become as a 90 degrees and 120 degrees, like that. The duration or starting instant is going to be different with respect to alpha. Now, we know the firing pulses as well. Next, what I have to do? We have to draw the line to line as usual, and we have to shade the output voltage waveform. So now the greens, whatever I represented the green shaded, that portion is your output voltage. Now the compare different you can notice when R is equal to 0 degrees, R is 30 degrees. R is 0, we started here and then we shaded this total portion and then it is shifted to AC and again shifted like this and shifted like this. But what is the different now? We can see one thing. Instead of you can starting point is different anyhow, here instead of starting here you can start here. Then I shade this 130 degrees, I mean only one, just this is starting and count 30 degrees, second verify. And one thing you can clearly notice that what is happening here, upper is anyhow still more positive, no different. So A phase means T1 device is conducting, but why earlier I transferred to AC, no, why I am not transferred to AC, even though C is more negative. That is the important thing you have to observe. What is happening? from this crossover onwards, C phase is more negative than B phase. But why I made it as a B phase only? Why I am not transferred to AB? See that this one, I mean C, AC. Why I am not transferred to AC after this crossover? Why I continue to AB only? The reason is from this point onwards coming down. If I come down here, this thyristor connected to which phase? There is a C phase. C phase device is T2. Whether T2 firing pulse is available here? No. Here pulse is available only from this point onwards. That's why here no firing pulse to the T2. Even though this is more negative, we cannot transfer to C phase. That's why AB only continue to conduct. I am continue to conduct here another 30 degrees. Then you can check it. What will happen? Firing pulse is available for T2. Then I transfer to A is still positive only. It won't be happen anything because unless it is more positive, it will not transfer to some other device. It will be continue to conduct. Now for lower group is going to be transfer after that point. Then it goes to be AC and will come to AC. Again you can see upper group device. What happening? A is less positive, but B is more positive. But why I am not transferred to B phase? The reason is A phase only it is continue to conduct, but B phase even though more positive, but no firing pulse at this point. If we come to down, the B phase is T3, no? T3 is available from this point. Here no T3 pulse. That's why the A phase only continue to conduct. That is the reason AC will continue to conduct. Once pulse is available for T3, then it is transferred to T3. Like that, all other phases is going to be conduct. So this is the way we have to represent for alpha is equal to 30 degrees. Similarly, you can see alpha is equal to 60 degree. I mention all the different values of alpha to try to understand. If you have any doubt, you ask me. It is very simple logic. Can start or blind way. You can see that every 60 degrees changeover is taking place. One thing is upper side, after that lower side, again upper side, lower side. So like that, every 60 degrees there is a one device is going to be changeover, whether it is a upper or a lower, but sequentially. First if it is changed upper, then immediately followed by lower, then again upper and again lower, like that. Now alpha is equal to 60 degrees. If alpha is 60 degrees, again same thing, firing pulses, you count 60 degrees and put the pulse. Starting point will differ, only starting point is differ. You can see this is 0 and then 30 degrees, then 60 degrees. So 60 means what? Alpha is 60 is nothing but omega t is equal to 30 plus 60, 90 degrees. There you can put the pulse, that way also fine. But one way you can follow alpha respective from the crossover points, you can count. And this is the crossover, count the 60 degrees, provide the firing pulse for T1. And this is 0 for T2, 30, 60 here for T2, then T3, then T5, all the things. Just you can count the from crossover onwards. This is the way you have to represent the firing pulses. Then you can draw the output. Same thing, you can starting point, we can start here. You can see here I am starting alpha is this is the T1 point. And now what is output at this point? Anybody answer me? At this point A is more positive, no doubt in that. And see that from this point onwards, what is the phase? C phase. C phase is more negative. C phase is connected to T2. Now why I am not transferred to C phase? Why I am not shading the AC? Because A is positive and C is more negative. According to our logic, the output will be AC. But why I shaded AB only? This is the AB line. I am not shaded the AC line. Anybody answered this question? Because C is connected to T2. At this point, even though this is more negative for the C phase, T2 device not having firing pulse. See that it is T6 is having pulse. T2 is available only from this. That's why you have to go for 6 device only, because this is the pulse is available, that means previous cycle. So here that is more negative B phase device that will continue to conduct up to firing pulse is available. That's why AB is your output. Once this point reached, what will happen? Now the pulse is available for the C phase negative device. That's why it is transferred to AC. Again, upper group device. You can see that this point, upper group devices also you can notice B phase is more positive than A phase, but A phase only continue to conduct rather than the B phase, because B phase firing pulse is available only here. That's why that will continue to conduct in the A phase. Like this, you can able to shade. From this, what is observation? It is reaches to the natural zero. This points reaches to the natural zero. Alpha is equal to 60 degrees. If I put alpha is 60 degrees, your waveform is reaches to the natural zero. Suppose if I make it alpha is equal to 90 degrees, what will happen? Starting point will differ. Instead of starting here, it will start here, but ending point will be what? Ending point will be natural zero. This is just a minute. Suppose alpha is 90 degree. Instead of starting here, we can start this point. Then this is your output, only this much portion. It is reaches natural zero, but pulse is not available at this to transfer to other. So it will be remains in the zero. And again, it will get like this. Again 0. And then it will get your output. So ending point is natural pi, that won't be happen anything, that will be remains there. And now we can see that this red line will be alpha is equal to 90 degrees. And still if I increase, then what will happen? Only the small portion, the negative portion, 0 portion will be more and will get like that. So that is the way we can able to represent your output voltage waveform. That shows here what is the range of continuous mode and what is the range of discontinuous mode of operation. For continuous mode of operation, 0 to 60 degrees. Alpha greater than 60 degree, it will go to discontinuous mode of operation for R load. Same thing, if I make it as RL, up to this is same, up to 60 degrees waveform will not change anything, even though if your load is a RL load. But what will happen for after 60 degrees? So that means this discontinuity portion, whatever 90 I drawn, no, this discontinuity portion will get like this. Will get like negative. Will get like this. This is the case of RL load. So anyhow, I will show that also. This is for alpha is 60 degrees. Now our expression, you can see that 0 to 60 degrees is a continuous mode of operation. Your average expression is very simple. 3 pulse converter, 6 pulse converter, no, 6 by 2 pi, then 3 by pi. So that's what I mentioned here, 3 by pi. And limits are what? How many? One pulse only can integrate. So what is the duration? 60 degrees. Starting point is alpha plus 30. So lower limit alpha plus 30 integral. Upper limit is what? Starting plus 60 degree. Alpha plus 30 plus 60. What is our output? AB, VAB. That's all. You will get it as a your average expression. Once if you make it limits like this, V out or VDC 6 by 2 pi alpha plus 30 to alpha plus 30 plus another 60 degree VAB. VAB is nothing but VA minus VB. VA is known Vm sin omega t. VB is Vm sin omega t minus 120. If you simplify that, you get it as a root 3 Vm sin omega t plus 30 degrees. And you can substitute here and integrate and substitute the limits. Then you will get it as a average output voltage for continuous mode of operation. You will get it as a 3 root 3 by pi Vm into cos alpha. 3 root 3 Vm by pi into cos alpha. This expression is valid for alpha range is less than or equal to 60 degrees only. And RMS anyhow you just whole power 1 by 2. And similarly for discontinuous mode of operation, this beyond the 60 degree discontinuous mode of operation will work out here. And now we can see limits will change. That's all. Where it is going to be natural 0, you can see this starting point. Somewhere we started here. Ending point is this. This ending point, if you see that omega t is at 150 degrees, it is going to be natural 0. What is our output we drawn here is a VAB. So therefore, alpha plus 30 to 150 degrees VAB, integrate it, we will get it as an average expression for discontinuous mode of operation. This is a discontinuous mode of operation. Earlier expression is valid for continuous, and suppose if I make it as RL load, then your expression is only continuous mode of operation. Previous expression V out or VDC, that is equal to 3 root 3 Pm by pi into cos alpha. This is valid for 0 to 180 degrees if it is a RL load. If it is R load means beyond 60 degree use this formula, and before 60 degree you can use this formula. So that is the case of RL load. Now we will show that this is the difference you can notice for RL load, 90 degrees case and 90 degrees case only for RL load. So what is different? This gap will continue to conduct because of energy stored in an inductor. That's why whatever we mentioned there, here R load case, this is fine. RL load case will get negative. This portion will make it like this. Now positive and negatives are same. You will get it as a average output will be 0 for exactly 90 degrees. And beyond 90 also is possible. I will show this here. You can see graph sheet how to provide the pulse separately. I mentioned here firing pulses IG1, IG2, IG3, IG4, IG5, IG6. This is the crossover for let it be IG1. Here based on our diagram, I mentioned as a diagram representation is different. In that fashion also IG1, IG3, IG5, and then based on, but our case I mentioned I think may be different. And anyhow, this is the T1, T3 in your case. This is a T5, and then lower group which is more negative, that device you can make it and provide the firing pulses, and you can shade your outputs. I used as a RYB notation. That's why we will get it as a RYB representation voltages. And similarly, if you want, you can use as ABC also. Same, both are same. And now we can see alpha is equal to, this is 30 degrees. We'll get like this, and alpha is equal to something 75 degrees. This is our voltage waveform, and then this is 90 degrees for RL load. This one is 90 degrees RL load, and this is a 120 degrees, because what will happen 120 here, one thing you remember, alpha is equal to 0 waveform is equal to alpha is equal to 180 degree waveform, only minus sign. Alpha is 0, what you have, this is your waveform, no, and alpha is 180 degree, in the negative side will get it. That is the both are same. 180 degrees is a maximum negative, 0 is a maximum positive, and this is alpha is 135 degrees. You go through this and carefully, if you have any doubt, you can ask me at any point of time. This is the alpha is equal to 135 degrees. And as usual, I mentioned VAB is nothing but root 3 Vm sin omega t plus 30 minus 90 or plus 90, like that. Different value, because while you are integrating, you may be required AB or B, C or C, anything you can integrate it. And same thing, alpha less than 90, already I derived root 3 Vm by pi into cos alpha. And this is the discontinuous mode of operation, only limits will change up to 180 degrees, and this is RMS. And the textbooks they mention like this. That's what I told now. If you, for clear cut explanation, we required to draw the phase voltages, pulses, then line to line voltages, and you draw the output. So that way it is easy. Now these are the different values of alphas, current waveform, and this is 150 degrees. All these things I mentioned. And this is the single 3-phase fully controlled rectifier or a 6-pulse converter. This one we call it a 6-pulse converter or a 2-quadrant converter. So we'll see in the next class. If you have any doubt, you can ask me. See, whatever doubts you have related to subject or any assignments or mid marks or anything, I am asking you clarify here itself. So that's the reason I'm asking you to ask at this point of time. After class over, many people are asking many doubts. Why I am waiting here, no? Whatever doubts you have, you raise now. I will clarify all the doubts. Anybody having issue with marks, mid marks or anything, you ask me. If you don't have any doubts, you can leave now.